move to the next point. We should ensure that whatever we see is clear.
That means work is being done. We can see that it is in opposite direction. It is against.
Hello, learners. You are welcome to another session of our e-learning on the subject physics. I am Napoleon Kure, and the topic we are looking at today is waves, part 1, on introduction of waves concepts. The outline is as follows. 1, wave and wave motion. Classes of waves, forms of waves, types of waves. Then we look at the terms that are used in describing waves. And we now have assignment. On the first outline, wave and wave motion, we look at what is a wave. A wave is a disturbance that carries or travels through a medium, transferring energy from one point to another in that medium without causing any permanent displacement of the medium or of the particles of the medium. And that is why we are talking about wave. On the other hand, wave motion is a process of transferring that disturbance. The process of transferring a disturbance. And that disturbance that is transferred carries energy along with it from one point to another. The energy carried along is kinetic energy. And it happens in a medium from one point to another, actually without transferring or maybe causing permanent displacement of the particles of that medium. The second outline talks about classes of waves. We have 2 classes of waves. Or we say waves is classified into 2. 1, mechanical waves and electromagnetic waves. What are mechanical waves? These are waves that do not require a material medium for their propagation, that is, for their taking place, for it to take place. We have such examples are as follows: water waves, sound waves, waves on a rope or on a string, and as many of them as possible. On the other hand, we have another set of waves which does not need a material medium, does not need a substance to have its propagation through. And what are those we refer to as electromagnetic waves? Waves which do not require a material medium for their propagation. An example of such on the list are light waves, radio waves, X-rays, gamma rays, and so on. Of course, we see that light from the sun does not need a material medium for it to reach us here. The same vein, whatever signal we hear from radio, whatever we hear from the radio, it transverses, space that does not contain air, for instance, and it gets to us. So, without a material medium, it can be transferred. That's just the distinction between mechanical waves and electromagnetic waves. There are many of them, but these are just few of them. Now, on the third part of our outline, we have forms of waves. And what are forms of waves? To look at forms of wave, we must look at what is responsible or how can this be demonstrated. We look at, first of all, what a ripple tank is. A ripple tank is a device that is used for producing and studying water waves in a laboratory. In a laboratory, we have a device or an instrument that water is in it and a disturbance is set up inside that device and waves are generated. Anytime you have waves generated, the source of that disturbance, the nature of that thing that causes that waves generation, determine the forms of wave that will be generated. And so we said a ripple tank is a device for producing and studying water waves in a laboratory. Waves that are generated from such a ripple tank system are of two forms. One, straight or plane waves, and circular or spherical waves. What do we mean by plane waves? Plane waves are said to be generated or formed when the object causing or generating the wave is a horizontal metal. That is when we said waves which are straight or plane said to be. Well, on the other hand, when the object causing the generation or the production of such a wave, if it is spherical, circular in nature, then we say such waves formed or produced are circular waves or spherical waves. Diagrams on this are as follows, shown below. Straight or plane wave, we have a source of disturbance, which is straight in nature. And once it drops into the ripple tank containing water, ripples are formed. And the nature or the forms of wave generated will be straight line. You can see the plane waves, vertical lines showing the waves that are produced in a plane or straight line form. Vertical. Well, the direction along which that wave travel is also shown. Horizontal lines with arrows. The arrows very important because it point the direction of journey or the propagation of the wave. And so we have plane waves and direction of the waves generated or traveling. Then on the other hand, when we have circular wave, as the name implies, is simply waves that are circular in nature. When the source, as we said, of disturbance is spherical, is circular, then we discover that circles, ripples in form of circular form. And we have source of disturbance in the middle, we have spherical waves, and the direction is spread around or through, spread out from the source. Now, we also have important concepts that must be understood under this waves part 1, and one of them is pulse. What is a pulse? A pulse in physics, it may have other definition or meaning and other things, but then a pulse is a sudden increase in magnitude of a physical quantity. But then it is shortly followed by a rapid decrease. Let's say a wave rises up, then suddenly it falls down. Is what we refer to as a pulse. It can happen, we say, physical quantity that the list has no end. On the other hand, we have another concept, a wavefront. What is wavefront? Wavefront simply means a line or a surface in the path of an advancing wave, on which all the particles on such a line or a surface are in the same phase or in the same state of disturbance. On the diagrams we have just shown, on forms of waves, straight lines, vertical straight lines that are there are what we refer to as wavefront. On the other hand, the circular lines we have there too are what we also refer to as wavefront. So any line or surface on which particles on such surface or line are in the same phase. What we mean by same phase, we are going to look at what a phase is. And so next is types of waves. And what is that? What to talk about types of wave, we must mention what we call progressive or traveling wave. A progressive or traveling wave is a wave that transfers energy in moving away from the source of the disturbance, as we have mentioned. And then we have two types of progressive wave, transverse waves and longitudinal waves. What are transverse waves? This simply means waves which travel perpendicularly to the direction of the vibrations producing the waves. If you have wave moving in a given medium and the particles of the medium vibrate up and down, not moving away from where they are, while the wave on the other hand is advancing, at 90 degrees to each other, that is what we refer to as transverse wave. The direction of waves, motion, and the direction of the vibration of the particles on the medium are at 90 degrees to each other. We refer to that as transverse wave. Such waves are water waves, light waves, radio waves, waves produced in a rope or string, and so on and so forth. A graph of such is shown below. A graph of displacement of vibrating particles about the mean position against time on transverse wave is shown below. On the graph, you can see two lines are clearly, boldly written at 90 degrees to each other, vertical and horizontal. Along the vertical, we have displacement, letter Y representing it, and we have time, distance also represented on the horizontal line. Now, we see particles on such, in the medium, will be moving up and down as the wave is transversing the medium. Some of the concept too will be defined as we look at terms, which is the last point or concept on the outline: amplitude, wavelength, and phase, trough. What do we mean by rate? On the diagram, we see the point where you have phase, that is at the turning point. That point, we call it a phase, and is simply referred to as a region of maximum upward displacement. Anytime a wave, transverse wave, is moving, it moves up, down. A phase is where you have the peak, and then under it, the one downwards is your trough. So the region of maximum upward displacement simply referred to as a phase, while the region of maximum downward displacement referred to as a trough. It's like they are diametrically opposite to each other, and that is what we have on transverse wave. On the other hand, we have longitudinal waves, and what are they? They are simply waves that travel in a direction. This time around, not perpendicular, not at 90 degrees, but we can say they are parallel to each other, to the vibrations of the particles of the medium. As the particles are vibrating, they are in the same direction with the journey or the direction of the wave traveling through. An example of such are sound waves, waves produced in a rope or string, and so on and so forth. Diagrams also illustrating longitudinal waves are shown below. Below are diagrams showing layers of air molecules before and during sound waves propagation. The first diagram there shows us those vertical lines are lines showing us the layers of air molecules. Air molecule before the sound propagates. Before sound starts traveling through the medium or through air, the layers are vertical. Now, what happens when sound is traveling through the medium? Air layers during sound propagation, on the other hand, those vertical lines before propagation of sound through air, representing the layers of molecules of air. You can see they are evenly spaced. The lines are evenly spaced. While sound is traveling, what happens is the molecules at the point we crowd together, we come together, and they form a region known as crest, represented as letter C. It's like an elastic, just like a rubber ring. You draw it, it expands, and then you allow it contracts. It's the same explanation we have here. They are elastic in nature. They come together, crowd together, then they spread out. Come together again, spread out. And as it is happening, the layers of air happening that way, sound is traveling through. That's exactly what happened. On this diagram, you can see that the C there represents compression. C is compression, where air equals rarefaction. Rarefaction is a concept talking about expansion of layers. Now, they are adjacent to each other. Compression, rarefaction, compression, rarefaction, compression, rarefaction. As that is happening, wave is traveling through, sound is passing through. Anytime somebody talks, that is exactly what happened in air. The layers come together, expand, come together again, expand, and successively, or we say consecutively, it goes that way and it moves on. It happened the same thing in solid. The vibration of the particle take place, and even in gas. So that is what we have. We say as sound waves travel, some layers of air molecules crowd together. They come together. and are known as the compression regions or areas, represented by letter C. Air density or air pressure at that point has a value above the normal pressure when it is not, when sound waves are not propagated through. We can see, go back to this diagram where you have layers of air before sound pass through it. You can see that they are evenly spaced. Now, when sound is passing through, they will come together at a point, as I said. The density, what we mean by density is simply anything divided by the surface area. If it is a line, you talk of line density. If it is area, you talk of area density, or maybe cubic density. Now, in this case, where you have the lines crowded together, the region occupied, there are more lines within a short place. So the density is higher than where you have the lines evenly spaced, occupied, maybe the same thing. If you have maybe 3 lines or maybe 10 lines in the same area with 5 lines, where you have the same area occupied by 10 lines, we say it is denser than the ones occupied by 5 lines because the regions are coincident. So we see that is of higher density. And then when you have, for rarefaction on the other hand, which are the regions, they expand. The density is less than the normal density. We take, for instance, before propagation of sound wave through the medium, it is said to be normal pressure or normal density. At the point of compression, the density is higher than the one before sound is traveling through. Then for the rarefaction, the density is lower than the one before propagation. So the normal one is in between. Denser is higher than the one that is rarefaction is lower. A longitudinal wave can be represented graphically. We can represent that one graphically by plotting the density or pressure of air molecules against position as shown. Apart from the other diagram show for propagation of sound wave through the medium, before and during, we can have a representation of the same, where you have graph of density or pressure of air molecules against position. Now you can see this is taking the form of our transverse wave. It's just for explanation's sake. The upward region there is your compression. The downward region is your rarefaction, and so on and so forth. Term used in describing waves. Below is a displacement time graph of a wave and positions or distances x of vibrating particles at instance. Now, we have a graph here of displacement, letter y, against distance x and against time small t. The wave, transverse wave, going through, at the beginning there, you have a molecule and we have different points where all those points there represent particles of the medium. From the beginning of the graph, where the y and the x or t axis intersect, the beginning, the wave generated there, and a molecule there also. When the wave is going up, at the upper region, one quarter wavelength is said to be lambda by 4, which is equivalent to 90 degrees. Then as it is going up to, touching it again, at the second point, you have lambda by 2. It progresses to the downward, where we talk of trough, as explained before now, is 3/4 lambda by 4. And eventually, by the time you come back, a wavelength has been formed. And now, where you have A, small letter A, small letter B, small letter C, small letter D are talking about positions or particles in a given medium when the wave is traversing through that medium. Where C is crest, T is trough, A is amplitude, and lambda is a Greek letter known as wavelength. The dots on the graph represent the positions of the particles at that instant. We say particles don't move, only the wave that move through the medium. And the arrows indicate the direction of motion of the particles. The particles' direction are indicated of the motion by the arrows. What are phase? Particles which are at the same vertical distance from the positions or rays and are moving in the same direction as shown on the graph. Like small letter A and small letter C, we say they are said to be in phase. Letter B and letter D are also said to be in phase because they are the same vertical distance from the horizontal axis and in the same direction. But where you have the same vertical distance but not in the same direction, we say they are said to be out of phase. Letter A, letter C are out of phase. Letter B, letter D also are out of phase. A cycle. A cycle is a complete to and fro movement or oscillation or rotation or revolution of a vibrating particle. Well, that's what a cycle refers to. Please, it's not the same as the normal cycle that is drawn. This one is CY-CLE. While the other one is CIR-CLE. Amplitude, lettered capital A, that's a symbol used, and it is the maximum displacement of a particle from its rest position. It is measured in meters. Wavelength, lambda represented, it is the distance between two successive crests or troughs, or two successive crests or rarefaction, or two successive points in phase of a wave. It is measured also in meters. Frequency, it is the maximum number of complete vibrations or cycles that a particle makes in 1 second. It is equivalent to the number of complete waves passing a given point in 1 second. SI unit is hertz. Period, it is the time taken by a wave to make one complete oscillation, the time measured in seconds. And the relationship between period and frequency, it is F equals to 1 over T. They are reciprocal each to the other. Wave speed is a distance with the wave travel in 1 second. SI unit is meter per second. A comparative analysis between cycle, wavelength, and units of plane angle measurement in degree and radian are given below. One cycle is equal to 1 wavelength, equal to 360 degrees, equals to 2 pi. 3/4 cycle is the same as 3 lambda by 4, 270 degrees, and 3 pi by 2. While half a cycle is the same as lambda by 2, 180 degrees, and pi. 1/4 cycle is the same as lambda by 4, 90 degrees, and pi by 2. With this, we come to the end of our lesson this morning. Introductory aspect of waves, which is an interesting aspect of physics. I would like you to pay attention. And I will call on my colleague, Mr. Buki Hassan, who will come to give you work to summarize it. I remain Napoleon Kure. Thank you.
Good day, learners at home. My name is Hassan Buki. I believe you have enjoyed the lesson that has been delivered to you by my colleague, Mr. Napoleon Kure, on the topic Waves, Part 1. But before we finally conclude the lesson for today, I will give you an assignment that will keep you busy at home. But before I give you the assignment, I will want you to take note of something very important. Try and differentiate between a wave and a wave motion because they look similar, but there's a difference between them. The wave is a disturbance. Wave motion is the process of transferring that disturbance. Assignment, question number 1. Differentiate between the following pairs of terms. A, wave and wave motion. B, mechanical waves and electromagnetic waves. C, plane waves and spherical waves. D, transverse waves and longitudinal waves. Question 2. Define the following terms as used in describing waves. A, phase. B, cycle. C, amplitude. D, wavelength. E, frequency, F, period, and finally G, wave speed. References, we have number 1, New School Physics by M.W. and Yakoha. 2, All-Inclusive Calculations in Physics by Solomon Dauda Yako. And 3, Senior Secondary School Physics by P.N. Okeke and M.W. and Yakoha. Now, if you want to reach us after your assignment or you have any other question to ask concerning the topic, you can reach Mr. Napoleon Kure on 080-3636-2105. Again, Napoleon Kure, 080-3636-2105. And Hassan Buki, 080-6550-4346. Again, Hassan Buki, 080-6550-4346. Stay home, stay safe, and keep learning. See you in our next lesson.